But not all data is normally distributed. Data is skewed, and particularly when we look at money examples, we see skewness, and so we look at those. So the way you think of it, you know, in terms of the reasoning and the thinking, of course, you say, oh, this is so basic. I know how to calculate means and standard deviations. I did it when I was 15. Yeah, I know. Yeah, that's not the point. The point is that we need to, what we bring to the table is our reasoning skills. So why do we have two measures of central tendency? Why do we need another measure of spread around our measure of central tendency? Is because a mean and a median are two types of averages, but a mean is not a good measure of central tendency when our data is skewed. And even at that basics, we can find examples, even with good journalists not understanding that. So essentially, this is what we have. You know, we have positively skewed, symmetric, bell-shaped, normal, but bell-shaped is not, normal is not just bell-shaped, there's other characteristics, and negatively skewed. Positively skewed or skewed to the right, small percentage of large values, skewed to the left, small percentage of low values. In this case, the mean gets pulled up towards these values, making it not a good measure of central tendency. A good measure of central tendency has 50% of values below it and 50% of values above it. So in skewed like this, the mean gets pulled up here, it's not in the middle any longer. Same over here. The small values will pull the mean towards it, meaning it's no longer in the middle. And so, therefore, it's no longer a good measure of central tendency. Because why do we need averages? We want good averages. So you can say, oh, yeah, 50% of people are going to get a salary below that value, or 50% of people are going to get a salary above that value. Yeah, that now we know what's a typical salary in a company. So you want the right, you don't want the mean, you know, when especially including CEO salary, it's going to be pulled up towards those salaries. So, that's maybe giving away a question I want to ask. All right, so a median is what we go with. So yeah, household income distribution is a good example. Only in this case, only 5% of people households earning more than $206,000 in 2014, for example. The median is like the 50th percentile. The middle value, so the median in that case is 53,700 in 2014. So that means that 50% of households have had an income below that value, and 50% of people had an income above that value. And so the median is always in the center like that. If you have an outlier, say 1, 2, 3, 4, and 30, the mean gets pulled up towards it. And so the mean will be 8 in that case. For the green line, and so the outlier pulls the mean. And it's no longer telling you it's only 20% of values are above the mean in that case. 80% are below. So therefore, it's not a good measure of central tendency, where it is in this case. Where the median is simply line up the values from the smallest to the largest. This is just a very simple hypothetical example. Line them up from the largest to smallest to the largest, and the median is just the middle value. If there is, say, 6 values, the median will just be 3 plus 4 divided by 2, which would be 3.5. If there was another value, like the value 6 here. So you can see the median obviously is always in the middle. It's only based on either the middle value or the 2 middle values divided by 2 after you line them up. So it cannot be affected by outliers because it's only based on the middle 1 or 2 values. And so therefore it's always a good measure of central tendency regardless of the skewness. There's just listing out how you go about getting it. So again, the median and the interquartile range that will come up next as a measure of variability around the median. Just 2 statistics that we'll deal with today for descriptive analysis, for discussing variability for a single quantitative variable. Again, this is all just tools for discussion and writing out reports and describing your data and summarizing your data and to see it that way. Even if this is a mathematical course where you have to do more calculations than in a reasoning course, it's still important to understand what you're doing. And so what's their purpose? All right, so that's just describing how you'd order them. And so very quickly, if you had values here, order them first, and then the middle 2 are these 2. Just add those together and divide by 2, and you get 8. And there's your median in that case. And so this is just the other example again. So, all right. So what do you think? This is the average sale price of a home in Manhattan last year was this amount, while the average sale price for a new home in the United States was this amount. The average they actually mention, and again, this is the New York Times and it's very basic, they're referring to as the mean. And if you go into the report, it gives you the median sale price for homes in Manhattan. It doesn't give us the median sale price for the United States. I'm not sure if that is the mean or the median in that case. But for Manhattan anyway, this was actually the mean. And so what do you think the distribution of apartment prices in Manhattan looks like? Is it normal, negatively skewed, or positively skewed? And so A, B, or C, you can throw it in the chat. You can all throw it in the chat. They want to be all part of it. Yeah, so we're seeing C's all the way here. I promise you the questions get more challenging. Yes, so C, positively skewed. So we think it's positively skewed. So just to annotate a little bit. Oh, good. All right, so you have we think something like that. So so the median, when we looked it up, when I looked it up, it was like the median would be somewhere in the middle here like that, you know, where 50% of values are above it. So the median, again, median was 837,000 or something. It just so where 50% of values are below it, if I move that over. All right, and 50% above it. I mean, oh, sorry. All right, so you get the idea. So that's 50% down here. Didn't get it exactly right. 50% up here. Whereas that's the median. When I had to look it up, but they used the mean, and so the mean was maybe, again, I'm just guessing. The mean could be around here, which was, again, the mean was 1.46 million, or if I could spell. And maybe it's a case that only 25% of values are above that value. Again, we don't know. Definitely it's skewed. So yeah, is there a question here or a chat or something? Yeah, so if the mean is to the right of the median, it is positively skewed. So you can refer back to that diagram that I just showed, and we can look at it again quickly. So please ask your questions, even if you ask them privately, so that everyone's on the same page. Like, we're all at different levels, and but some people have taken stats before, some people haven't. So let me just clear off all of this. So yeah, so anyway, before I do that, I'm just kind of suggesting that the 1.46 million, the mean is getting pulled up by these extraordinarily large housing prices, apartment prices. And we'll look at the classic one that's still going up. I can see it from my rooftop. We'll look at the price of that one. And so these extremely high prices pull the mean up towards it, and the mean here, where the median will always remain in the center, no matter how skewed it is. So that's important to know, and it's because in the equation for the mean, you're going to have much larger values, like at the top, divided by the same sample size. It pulls that value up towards it, where the median will always remain in the middle. So positively skewed, as we said. So yes, this one is an outlier, and yeah, it's still going up. So what effect do you think this apartment will have on the mean? Well, we've already clear on that. It's going to pull it up towards it, and the median will remain the same. So that's pretty already your answer. So 238 million to watch the birds fly by. Okay, it's a lot of money for an apartment, but anyway, that's the outright winner as outliers go in Manhattan. Anyway, all right. So the interquartile range was mentioned in the earlier on. That is another measure of variability. Is a measure of variability around the median. So quarters. Yeah. So you need to know how to construct one of these box plots for homework questions and for midterms, and understand what's considered an outlier in a box plot. Yeah, so it's all about splitting your data into quarters. And so a median was like splitting your data into half, at 50% below the median and 50% of the data values above the median. So the quartiles are splitting it into quarters. Think of it that way. The median is a value in your data whatever your data is, whatever quantitative data you're dealing with, it's a value where 50% of values are below it and 50% of values are above it, no matter what the distribution, shape of your distribution of values. Then quartiles are just, Q2 is the median, the second quartile. So you are splitting, getting two more values, Q1 and Q3, and Q2 is your median. And where the value Q1 is where 25% of values are below it and 75% are above. Q2 is the median, 50% of values are below it, 50% of values are above it. And Q3 is 75% of values are below it and 25% of values are above it. So it's two more values you know, three in total that are splitting your data into quartiles. Okay, so seeing it with a simple hypothetical example, find your median. After you line up your values from smallest to the largest, find your median. And so in this case, this is it here. There's 9 values. It's an odd number of values. It's the middle value. I said if there's even number of values, like there was another value like 50 here, it would be these two divided by 2. So line up your values from smallest to largest. Then the median is the value here. That's your Q2, or the median. So now you're going to focus on the lower half of the data and include your median. When you have an even number of values, when you have an even number of values, just include your median. Or an odd number, you have an odd number of values, like 9 here, and the 5th value is the median. Include the median in the lower half, include the median in the upper half. When you have an even number of values, just split it in 2. If there was 10 values, it would be 5 and 5. But when there's an odd number of values, include the median in both halves. Then just get the median of the lower half, which is the middle value of the lower half of values, and that's Q1, and that's 7. And then up here, for the upper half, get the middle value for those, which is the third value of the upper half of the data, the upper 5 values, including the median, which is equal to 19. So anyway, this is just a small data set just to see how you calculate these things. And what you have here then is the median, the interquartile range is just simply Q3 minus Q1. So I see a couple of hands there. Alex, your hand is still up, but maybe it's Daniel's. I don't know which one's. Is it Daniel?
Yes, I think so. Thank you.
Yeah.
Yes, thank you. So my question is just, what precise quartile range telling you? It's not telling you the same thing as like a median value. So I'm wondering if there's some way to pin down a little more clearly what information you're getting from that number. Okay.
All right, we'll get to that. I want to first just show you how to calculate it, and so that's how we calculate it with just a hypothetical data set. And so next is, I'm glad, do interrupt me with those, not interrupt me, but ask me those questions. So like I'm trying to show you now in taking those values, like and then looking at the interquartile range visually, and we'll see it here actually. If you look briefly here, Q3, this is systolic blood pressure. Q3 is where 75% of individual blood pressures are below the Q3, 138. And 25% of values are below the Q1. And so we'll look at it visually, but it's saying that 50% of diastolic blood pressures, of individual diastolic pressures in our data set are between, the middle 50% of values are between 121 and 138. And so it is a measure, it's a measure of variability around the median value, which is 132, that is unaffected by outliers because it's only based on the middle 50% of data. So if this turns out to be an outlier, but as a measure of variability in the data, it's not affected by the outliers. So just like the median is not affected by outliers, the interquartile range is not affected by outliers. As a measure of variability, it's not affected by outliers.
Got it. Thank you so much.
Okay.
That's very clear.
Okay, so basically, you can read about how to construct a box plot. I'll go through it quickly and briefly now, and then I'll take my time and explain it at the end of class the next day, not to rush this too much, or the beginning of class the next day. but you can step by step, you can see how to do it. I'll use the last 2 minutes, and then I'll shoot you out to breakout rooms, and there's some popularity there, and I'll continue doing it while it's still popular, but otherwise you can leave. But let me just take the 2 minutes just to explain what a box plot is, and then do it again the next day. And so take all this diastolic blood pressure down here. Horizontally, you can do these vertically for comparison purposes, which we'll talk about the next day, comparing box plots, comparing distributions with box plots, or like the football example we look at. But to look at one on its own, where we begin, lay it horizontally is the easier way to understand it. So what you have here is the number line, range of the values. We saw the range of the values were from 108 to 200 systolic blood pressures, min to max. And so it is a nice alternative to a histogram to see what the data is telling us. And so it's splitting it up into quarters, but you start with the median here. And I go through it very quickly in the last minute, and then I'll stop. Draw a line for the median right here in the middle, which is 132. And then draw a line for 121 and 138. 121 for Q1, 138. Finish off the box. And what we've got here is a box representing the interquartile range. 50%, the middle 50% of the diastolic blood pressures are in this interquartile range of 121 to 138. Okay, again, kind of running out of time, but out here you see this dotted line. This is like an imaginary line. We draw it. You go up here to Q3, and then Q3 plus 1.5 times the interquartile range. And the interquartile range is, you can see it more clearly, 138 minus 121, Q3 minus Q1 is 17. So 1.5 times 17 above Q3 is where you draw this line, and that line is imaginary line, and any values above it are considered an outlier. This is a new convention, extreme outlier, but any values above it are outliers. Now I'm going to stop there, and I'll continue from there the next day to finish explaining this and read through that, and then we'll discuss it a bit more, and then we'll compare histograms, and compare box plots, and then the football example, we'll look at that. Compare histograms with box plots just to see what one gives you over the other, and a couple of examples of that. And then there's a question that might throw you out to a breakout room, and then we'll cover the rest of it. We'll get into the normal distribution the next day. All right, so is there any last question? I know Friday is a tough one to turn up for, but thank you for turning up. Otherwise, I'm going to say goodbye to you, but I'll throw you out into break rooms. Again, as long as it's popular, I'll continue it. So just to kind of get you to collaborate, work together if you want to, and maybe meet someone that you never would have met otherwise.